Hello everyone, welcome to this lecture. In the last few lectures, we studied modal parameter estimation using frequency domain methods. In this lecture, we are going to study modal parameter estimation using time domain methods. And specifically, we are going to study in detail the time domain method of eigen system realization algorithm, okay, which is abbreviated as ERA. So, let us first of all briefly look at what is the idea behind time domain methods of modal parameter estimation. So, time domain methods of modal parameter estimation, they are based on impulse response functions. Okay. So, the time domain methods perform curve fitting of impulse response functions, and earlier we have studied that the impulse response function of a multi-degree of freedom system consists of contributions from all the modes of the system. So, for case of a multi-degree of freedom system with viscous damping, we saw that the impulse response function is contributed by n number of complex conjugate mode pairs. So, this is the expression we derived earlier for a multi-degree of freedom system with non-proportional viscous damping. So, here this Hjk, okay, it is the impulse response function, okay, and which is defined as the response at jth coordinate due to unit impulse applied at the kth coordinate. So, that is nothing but the impulse response function Hjk, and then it consists of contributions from n complex conjugate mode pairs. Okay. So, each physical mode of a multi-degree of freedom system with non-proportional viscous damping is described by two complex conjugate modes, right, and therefore, if there are n physical modes, there would be 2n number of complex conjugate modes, that is n number of complex conjugate mode pairs. Okay. So, we see from here that on the right hand side we have the modal parameters which are appearing, right. For example, these are the mode shape elements and SR is the eigenvalue of the rth mode, and these are the quantities corresponding to the complex conjugate mode, right. So, and then SR star is the complex conjugate eigenvalue. So, in this way, if we know the impulse response function, okay, if we obtain it by measurement, then we can feed this expression to the measured impulse response function and identify the modal parameters in the process, right, by curve fitting. Now, how the impulse response function can be obtained by measurement? So, we know that impulse response function is defined when a ideal unit impulse is applied at any particular degree of freedom, right, with no input or force applied at other degrees of freedom. Now, application of an ideal impulse is very difficult in practice, because if you recall, the ideal impulse is defined based on the Dirac delta function, which requires applying a force over an infinite simul duration of time, and the value of the force should be infinite. So, that is the ideal unit impulse, right. So, achieving this ideal conditions is difficult in practice, and that is why it is generally difficult to measure impulse response function directly. Therefore, an indirect method is used, in which what we do is that we first measure the frequency response function. Okay. So, we can measure the frequency response function alpha jk and then take its IFT, that is inverse Fourier transform, in order to obtain the corresponding impulse response function. So, there are now several time domain methods like complex exponential method, that is one of them. Then there is least square complex exponential method, there is Ibrahim time domain method. So, there are a few other methods. There is also a method called eigen system realization algorithm, and that is the method we are going to study in more detail today. So, the eigen system realization algorithm is a time domain multi input multi output method. Okay. So, this method can take into account the time domain response at multiple locations due to multiple inputs applied on the system. So, all these responses which are measured at multiple locations due to multiple inputs being applied can be processed simultaneously using this method. So, this eigen system realization algorithm is based on system realization approach, which is used in control theory, right. So, in which a state space model of the system is first identified. So, this eigen system realization algorithm is based on the system realization approach, in which first of all a model of the system is realized, right, specifically the state space model, and then the state space model is solved in order to obtain the modal parameters of the system. So, let us now look at the formulation of the method. Okay. So, in this method the discrete state space matrices are first identified from the free pulse responses. Okay. So, the free pulse responses are nothing but the impulse responses in discrete time. So, because the data we measure in practice is discrete, right. So, it is a discrete signal, a discrete time domain signals we measure. and therefore, from the discrete time domain signals or discrete pulse responses, we obtain first of all the state space model of the system, and because the data is discrete, the model that is obtained is also discrete, right, and then from the discrete model obtain the model parameters of the system. So, the main steps we are going to follow in the formulation are as follows. First of all, we will look at what is the state space model of the system in the continuous time domain, okay, continuous time state space model. From the continuous time state space model, we will develop a discrete time state space model, okay, and then we will look at what are the free pulse responses. So, we will determine the free pulse responses from the discrete state space model, and then we will see that what is the relationship between the free pulse responses and the system model, right. What is the relationship between the state space matrices and the free pulse responses, and then using that relationship we will determine or we will realize the system state space model, okay. So, we will see that how state matrix can be determined from the pulse responses, and once we have the state matrix, then we will see that how we can determine model parameters from the state matrix. So, these are the steps which are there, and now one by one all these steps we will study in more detail. So, let us first of all look at what is continuous time state space model, right. So, earlier we have studied what is state space model when we studied eigenvalue problem for a multi-degree of freedom system with viscous damping, specifically the non-proportional viscous damping. We saw that we first developed the state space model and then we defined eigenvalue problem based on the state space model. So, this is the equation of motion for a multi-degree of freedom system with viscous damping. So, here you can see it is mx double dot plus cv x dot plus kx is equal to f. So, here you can see we have used the symbol cv to represent the viscous damping matrix, because later we are going to use symbol c for representing the output matrix, and that is why in order to make a distinction we are using the symbol cv here to represent the viscous damping matrix. So, now these are the second order equations, right, these are second order differential equations. So, now we can obtain state space model from this, okay. For that then we need to choose the state variables, right. So, this system is of order n, right, the degree of freedom of the system is n. So, we require 2n number of state variables to choose, and then we will choose the displacement and velocities at the n degrees of freedom as the state variables. So, this is the state equation for the state space model, right. So, here y is the state vector, this is nothing but a state vector, okay. U is the input vector, so currently we assume that there are inputs acting at q number of degrees of freedom, right. So, it is of order q by 1, and then the AC is the state matrix and BC is the input matrix, because it is the coefficient of the input vector. So, here we have used the subscript C in order to represent association of AC and BC with continuous time state space model. And then this is the output equation. So, this is the output equation, and this of course is the state equation. So, this output equation here now Z, the output vector, Z is the output vector, right, and C is the output matrix, okay, and then there are outputs corresponding to p number of degrees of freedom, right, that is why its order is p by 1. So, therefore, this state space model connects the inputs applied at q degrees of freedom, right, with the outputs at p degrees of freedom, okay, through state vector. So, y is the state vector which describes the state of the system at any instant of time, okay. So, therefore, by solving the state equation we would be able to know how the state of the system is evolving with time when the inputs are applied, and once the state vector information is available, then from the state vector we can determine the outputs of interest of the system, right, in this case Z contains that information. So, this is basically the state space model in the continuous time. Now, the state equation is, they represent 2n number of simultaneous first order differential equations, right. So, we need to first of all solve the state equation, and then the output can be easily determined by substituting the state into the output equation. Now, how to solve state equation? So, there exists an integral solution, okay, an integral solution of the state equation is available, and equation is that solution is given by this. So, you can see y of t is the solution of the state vector, right. So, this is nothing but a solution, and on the right hand side there are two terms. The first term you can see here, this first term depends on the initial condition on the state vector. So, you can see this y t naught, okay. So, this is nothing but the initial condition on the state vector, and this term therefore determines the component of the response due to the initial state of the system. And then the second term, it depends on the input which is acting on the system. So, you can see here this is the input vector u tau, here tau is the dummy time variable. So, therefore, this is the input vector. So, this second term quantifies the response, right, due to the input acting on the system. So, this is the integral solution. So, once the input vector is specified, the integration can be carried out and the solution can be determined. So, let us now see that how we obtain the discrete state space model. So, we are now going to use the solution we obtained in continuous time in order to obtain a discrete equation relating the state vector and the input vector and the initial state on the system, right. So, here now we are going to consider time as a discrete quantity, no longer time is continuous, okay. So, let us assume a certain sampling frequency, right. So, once the sampling frequency is chosen, the time interval between two samples, which is delta t, will be fixed, which will be equal to 1 by fs. So, and let us now consider two consecutive time instants. So, you can see this is the time axis, and let us say these are the discrete samples, right. So, we are considering now the time instant t k. So, this is the time instant t k, and then this is the time instant t k plus 1. So, we are now considering two consecutive time instants, and the time interval between the instants is delta t, right, this is delta t. So, let us consider the instant t k given by k into delta t, and then t k plus 1 which will be equal to k plus 1 delta t. So, these are two consecutive time instants, right. So, now we treat t k instant as the initial time t naught, okay, and we treat the next time instant the t k plus 1 as the future time t. So, now we can replace t by k plus 1 delta t, right, and t naught we can replace by k into delta t. So, when this is done, we get this equation, right. So, you can see now we have replaced t and t naught by the corresponding discrete times. Now, let us do a change of variable. So, let us change a variable from tau, which is the variable of integration here. You can see this is the variable of integration tau. Let us change that variable to gamma. Now, we replace tau in terms of gamma, right. So, we write tau is equal to gamma plus k into delta t, and then we simplify the equation, and we obtain these results. So, we are representing the term e to the power ac delta t by matrix A, and we are representing this complete integral, right, which simplifies to this term, right, by matrix B. So, when these changes are incorporated, we basically get this equation, okay. So, this is the state equation in discrete time, this is the state equation in discrete time, okay. So, here what we see that the state at a future instant, that is at the k plus 1th instant, it depends on the state vector at the kth instant and the input vector at the kth instant, and A and B are state matrix and input matrix in discrete time, right. So, here A is the state matrix in discrete time, right. Similarly, B is the input matrix in discrete time, and now yk is the state vector in discrete time. Similarly, we can now write the output equation. The output equation is given by zk is equal to c into yk. So, once the state vector is known at a discrete time, we can obtain the corresponding output vector at that discrete time. So, these two equations together form the state space model of the system, right. So, this is the output equation in discrete time. Let us now obtain impulse responses using this discrete state space model. Okay. So, now the impulse responses in discrete time are referred as free pulse responses, right. So, impulse response function is in continuous time, okay, and the corresponding quantity in discrete time often referred as free pulse response. To obtain free pulse response, we need to apply a unit impulse at a degree of freedom, right, and then look at for the response at the other degree of freedom. So, let us now determine the free pulse response for the first input location. So, what we do, we apply unit impulse at the first input with no force at other inputs. Okay. So, now we are going to apply a unit impulse at the first input for the first instant of time. After that, there will be no input. So, therefore, we write uk, that is the input vector uk, as vector delta 1k, right. So, delta 1k is defined like this. So, here you can see delta 1k is a column vector containing inputs applied at all degrees of freedom, and we see from here that input at the first degree of freedom is 1 and input at all the other degrees of freedom is 0, correct. And then this is at first instant. So, you can see at the beginning, at the first instant, this is the situation, and now for the next instant there is no input at any of the degrees of freedom, correct. So, this is the delta 1k for k more than 0, right, while this first one is for k is equal to 0. So, at the initial instant, at the first instant, we have a unit impulse applied at the first degree of freedom with no input at other degrees of freedom, and then for all the future times, that is k is more than 1, there is no input at any of the degrees of freedom. Okay. So, this constitutes a application of unit impulse at the first degree of freedom with no input at other degrees of freedom. So, this is therefore the definition of delta 1k. Therefore, input vector is vector delta 1k. And now what we would do? We would try to determine what is the response of the system. Since we have the discrete state space model, now we can determine the response of the system from the discrete state space model using this as the input. And we will also assume 0 initial conditions, right. So, system is at rest when this input is applied. So, the state vector at time t is equal to 0, right, or t is equal to t0 is 0, right. So, therefore, now we use the discrete state space model and then try to determine what is the response, what is the state vector, and then the output vector at k is equal to 0, right. So, if we recall what was the equation, okay, the equation was the discrete equation was y k plus 1 was equal to matrix A times, so this is a vector, right, into vector y k plus b into u k. So, this was the state equation. So, now when we substitute k is equal to 0 in this equation, what we would get? We would get y 1, right, is equal to vector of zeros, because y 0 is 0 plus b into u 0, right, and u 0 is nothing but delta 1 0. So, this will be delta 1 0, correct. So, you can see here, that is why we get y 1 as b into delta 1 0, correct. And then we have the output equation. The output equation is vector z k is equal to matrix C multiplied by y k, correct. And because so k is equal to 0 means z 0 will be equal to matrix C into y0, y0 is the initial state of the system, it is 0. So, this becomes a vector of 0. So, you can see in this way we get the output, correct. So, you can see it is very easy to solve the discrete space model once the input is specified. So, this is the state of the system at instant 1, that is the next instant, and what is the output at the previous instant, right. Now, we repeat this process for k is equal to 1. So, you can see this is for k is equal to 1. So, therefore, the state vector at the next instant is y2, and that is equal to a into b into delta 1 0, and the output z1 is c b delta 1 0. So, in this way we can proceed, right, further, and then we can write a general expression for the state, okay, and the output, and those expressions are this. So, yk can be shown to be equal to a k minus 1 into b into delta 1 0, and zk can be shown to be equal to c into a k minus 1 into b into delta 1 0, right. Similarly, now if we apply the input at the second location or the second degrees of freedom, then what will happen? We will have to define a new input vector, okay, and that input vector would be uk would be equal to delta 2k, right, and delta 2k is defined similar to how delta 1k is defined. So, delta 2k for the first instant will have a unit impulse applied at the second degree of freedom, and no impulse or no input at the other degrees of freedom, and for all the future instants the input at all the degrees of freedom would be 0. So, when that is done and then process is followed, we get these expressions, that how the state vectors and output vectors are related to the input delta 2 0, right. So, you can see here these are the expressions with delta 2 as the input, okay, while these were the expressions with delta 1 as the input, isn't it. So, in this way we can obtain the free pulse response when input is when the impulse is applied as any particular degrees of freedom. So, we can similarly find delta 3, delta 4 and delta q, right. All the we can determine all the free pulse responses corresponding to all the input locations we can determine. So, now what we are going to do is we are going to now combine all these pulse responses, okay. So, we can form a matrix of pulse responses. For example, if Z is the matrix, then I can write this matrix as the first of all we can have the pulse responses due to input applied at the first location, and if we call that as Z1, right, that is the first column. Then the second column is the vector of pulse responses due to input applied at the second input, right, and in this way we can stack all these columns of free pulse responses, right. This is corresponding to Q, isn't it. So, you can see there are such Q columns, and then because the responses are measured at the p number of outputs, so the number of rows in this matrix would be p. So, therefore, this matrix will be of size p by q. So, it is a matrix of free pulse responses, okay. And then what we can do? We can substitute the expression for the free pulse response Z, right, corresponding to a particular input location into this matrix, right, and then which basically leads to this result, okay. So, you can see here now this is the matrix of free pulse responses, okay. So, it is a matrix of free pulse responses, isn't it. And you can see this coefficient matrix C A k minus 1 b is common to all those columns, all those free pulse responses, and that is why that has been taken common, and then this finally therefore reduces to this expression where I is the unity matrix, okay. So, effectively what we get, that Zk is equal to C A k minus 1 into b, right, that is the expression we get for the matrix of the free pulse responses. And we note that this matrix is dependent only on the system matrices A, B, C, right, because it contains the information about the impulse responses, and impulse responses, which are the free pulse responses in discrete time, they characterize the system, they make the system properties, right, and that is why they would not be dependent on the inputs, they depend only on the system characteristics, and that is why this matrix of free pulse responses is related only to the system matrices, that is A, B, C, right. So now what we are going to talk about is that how the system can be realized, how the system can be realized from this matrix of free pulse responses, right. How the system matrices or specifically the state matrix can be determined from this matrix of free pulse responses, because in practice we expect that these free pulse responses would be available from measurement, and then the question arises that how do you determine the state matrix of the system from this information about the pulse responses obtained by measurement. So, let us now look at what is system realization, or how to realize the system matrix from matrix pulse responses. So, in this method we first construct a matrix which is called Bloch-Hankel matrix, okay, using the free pulse responses. So, this Hankel matrix is given by collection of these free pulse responses. So, you can see we first of all have in the first row this is the free pulse response matrix we saw on the previous slide, and now what we do, this is at a certain instant, right, at a certain instant in the discrete time space, right, and now we advance the instant by one interval, right. So, at the next instant again we can obtain this matrix of free pulse responses, and that is nothing but a free pulse response matrix zk plus 1, is not it. Then we similarly obtain such free pulse response matrix at other instants, right, and in this way we take the free pulse response matrix at s number of instants. So, this is the free pulse response matrix at the sth instant, which is designated as zk plus s minus 1. So, in this way this first row of the Hankel matrix is constructed. It consists of free pulse response matrix at s number of instants taken stacked as columns. We now advance all these s instants by one time interval, okay, all these s instants we advance by one time interval, and then we use the free pulse response matrix corresponding to those s instants and then construct the second row of the Hankel matrix. So, that is why you can see the first element in the second row is the free pulse response matrix zk plus 1, which is the pulse response matrix at k plus 1, right, and then the next one is zk plus 2, and the last element in this row is at k plus s, right. So, in this way we take r number of rows to construct this Bloch-Hankel matrix, and that is why the order of this Hankel matrix is PR into QS, okay. So, there are p number of rows in each pulse response matrix Z, and there are such r number of rows, and that is why there are total p into r number of rows, that is PR. And then there are q number of columns in each free pulse response matrix, and there are such s number of columns, and that is why the total number of columns is QS. Now, if we substitute the expression for the free pulse response matrix we got, right, in this Bloch-Hankel matrix, then we get this result, right, and then we can write down the Bloch-Hankel matrix in this form. Okay. So, we have, you can see first of all a matrix here, then we have another matrix here, and then we have another matrix here. Okay. So, we can divide the Bloch-Hankel matrix, or we can write the Bloch-Hankel matrix as product of three matrices. So, the first matrix is basically matrix Q here, you can see this is the Q matrix, this one, and this W matrix is the last matrix here in the equation, and this A k minus 1 is of course this matrix. So, the matrix Q and W are the observability and controllability matrices. The Q depends on the matrix C, and matrix C is the output matrix, and when we take measurements at the output locations we are observing the system, right, we are getting information about the system, which means we are observing the system from through Q C matrix, and that is why this Q matrix is called observability matrix. If we look at matrix W, then it depends on matrix B, which is the input matrix, right, and input at the Q locations X through this matrix. So, if we have to control the system, then through these q input locations we can control the system, right, and therefore this W matrix determines the way system can be controlled, and that is why it is called controllability matrix. So, in this way a Bloch-Henkel matrix has been constructed using the free pulse responses written down in terms of 3 matrices, that is Q, A, K minus 1 and W. Now, the next question is, how do you realize this matrix A using this Bloch-Henkel matrix? That is something we are going to now study. So, now from the Bloch-Henkel matrix, it is seen that there could be infinite realizations of the state matrix which may reproduce the free pulse responses, but then which is supposed to be the true representation of the system. Although free pulse responses are reproduced, but do all of them represent the system? So, the question is that which one, which realization represents the system truly. So, the system matrix which is of the lowest order, okay, and which can also reproduce the pulse responses, the free pulse responses, is supposed to be the true representation of the system. Okay. So, all the infinite realizations may reproduce the responses, but they may not represent the system truly, because they may contain many additional poles which do not belong to the system, right, and therefore the state matrix which is of the lowest order, the minimum order, is supposed to not only reproduce the measured responses, but it also is supposed to include only those poles which belong to the system, and that is why we try to find a minimum realization of the system. So, the minimum realization corresponds to the state space matrices which are of minimum order. Now, here the eigen system realization algorithm makes use of the singular value decomposition, okay, in order to determine the minimum order of the matrices. Now, at k is equal to 1, we can write the expression for H naught as q into W, because a k minus 1 at k is equal to 1 would be a to the power 0 would be 1. So, that is why we get H naught is equal to q into W. And now we find the singular value decomposition of matrix H naught. So, you can see earlier we have studied what is singular value decomposition. Okay. So, here this U is a matrix of left singular vectors, right, and V is a matrix of right singular vectors. V is a matrix of right singular vectors, and S is a matrix of singular values. Okay. This is a matrix of singular values. Okay. And we see that the order of the singular value matrix is same as the order of the Henkel matrix. Okay. So, it is a rectangular matrix and the size is PR into QS. So, now how to obtain the minimum realization? So, this matrix S would contain many singular values which are either 0 or nearly equal to 0, right. So, all such singular values we drop, okay, and then we truncate the singular value matrix, and then we also truncate the U and V matrices which contains the singular vectors. So, the singular values which we drop, the corresponding left and right singular vectors also drop from the corresponding matrices, and this way we then get a truncated matrices U, S and V. Okay. So, by doing so we get this result. So, you can see on the right hand side the order of the matrices U, S and V, they are now reduced. So, you can see here the matrix S is now of order 2n by 2n, because now we here we have retained only the 2n number of singular values which were found to be non-zero, right, while all the rest of the 0 or nearly 0 singular values have been dropped, and corresponding left and right angle singular vectors have also been dropped. So, this truncation essentially leads to minimum realization, right. This has been done to obtain a minimum realization. We can further write the singular value matrix S as S to the power 1 by 2 into S to the power 1 by 2, and now we compare this equation with this equation. Okay. If we compare these two equations, then we can say that Q is equal to U into S to the power half and W is equal to S to the power half into V transpose, is not it. Now, similarly at k is equal to 2, we can write the expression for Bloch-Henkel matrix as H1 is equal to Q into A to the power 1 into W, right, and now we can substitute Q and W from these expressions, right. This q and w expressions we can substitute here, this is q and this is w. So, when that is done, we get this expression after shifting all the matrices other than A to the other side of the equation. Okay. So, this is the equation to obtain the state matrix A, right. So, this is the equation to realize state matrix A. Okay. So, with this equation we can find the state matrix, and what we need to find the state matrix using this equation, we first of all need the singular values matrix S and matrices U and V, which are the matrices of the singular left and right singular vectors. And how we obtain that? So, what we do, once we have the free pulse responses measured at all the outputs of interest, at output locations of interest, then we choose now two instants, two consecutive instants. At the first instant, using the free pulse responses at the first instant, we first construct the Bloch-Hankel matrix H naught, right. We construct the Bloch-Hankel matrix, and that is referred as matrix H naught, is not it. And then we perform the singular value decomposition of that matrix, and then we drop the 0 and nearly 0 singular values from the singular value matrix, and we also truncate correspondingly the matrix of left and right singular vectors. Once that is done, the matrices we get, those are nothing but the truncated singular value and truncated U and V matrices, which are to be used in this final equation. So, in this way we obtain the matrices S, U and V. Now, for the next time instant, right, we again construct the Bloch-Hankel matrix, and that matrix is referred as matrix H1. Okay. So, that matrix is designated as matrix H1, and that is something which is also used in this equation. So, you can see in this way we get S, U and V, which are required in this equation, and we also get H1, the Bloch-Hankel matrix. Once that is there, now we can compute the state matrix using this expression. So, once the state matrix is obtained, the question is how do you obtain the modal parameters. Okay. So, now this state matrix we have realized it is in discrete space. Okay. This is the equation to realize state matrix, and this matrix A here is in discrete time. Okay. So, what we do, we first of all solve the eigenvalue problem using this discrete matrix. Okay, that gives us the eigenvalues and eigenvectors, and then next we convert these eigenvalues and eigenvectors from discrete time space to continuous time space. So, therefore, how we find modal parameters? We first find eigenvalues and eigenvectors of the realized state matrix, okay, and let these eigenvalues and eigenvectors are represented by SRD and psi RD. So, here D has been used to represent association of these eigenvalues and eigenvectors with the discrete state space model, right. And now, previously we got a relationship between the state matrix in continuous time and state matrix in the discrete time. That same relationship can be used to convert the eigenvalue from discrete time to continuous time. So, here SR is the eigenvalue in continuous time, right, while SRD is the eigenvalue in discrete time. Okay. So, from here we can find SR, because the system in practice generally are underdamped systems, and therefore, these eigenvalues would be appearing in complex conjugate pairs, right. So, from the complex eigenvalue we can obtain the natural frequency and modal viscous damping factor, right, as we studied earlier, right, because we know that a complex eigenvalue can be written as minus zeta r omega r plus I under root of 1 minus zeta r square into omega r. So, we from the real and imaginary parts of the eigenvalue we can obtain the natural frequency and the modal viscous damping factor, right. And the eigenvector in continuous time. So, this is the eigenvector in continuous time. is related to the eigenvector in discrete time through matrix C, which is the output matrix, and this output matrix can be obtained from this relationship, which also has been obtained from the system realization theory, right. So, it is equal to E p transpose u into S to the power half, right, and E p is given by this expression. It consists of a identity matrix and null matrices. Okay. So, this is the output matrix. So, then we can substitute this output matrix in the equation and then find the eigenvectors in continuous time, right. So, in this way we obtain the modal parameters from the measured free pulse responses. Let us now take an example to get further insight into the various steps which are involved in implementation of the eigen system realization algorithm. And here now we are going to again consider a simulated example of the cantilever structure which we have studied in previous simulations, right, of the different modal parameter estimation methods. Now here in this example we are going to make use of the free decay responses instead of the impulse responses. So, impulse response is also a free vibration response because we apply the impulse and the structure vibrates freely, right. Free decay responses are also the free vibration responses, but they do not correspond only to the impulse being applied, they may correspond to other types of initial disturbances. Okay. So, this ERA can handle both types of free responses, whether they are impulse responses, free pulse responses, or the free decay responses due to other types of excitations. So, therefore, we are going to make use of the free decay responses in this example, and then we are going to use a multi input excitation. Okay. At multiple points we are going to apply inputs, right, and then use the resulting free decay responses to perform the modal parameter estimation. And then specifically we are going to use a band limited white noise excitation over a frequency range of 0 to 400 hertz. Okay. So, a band limited white noise is generated over this frequency range, and then that is used to excite the system, right, and these excitations are applied at test points 2 and 5, okay, for a duration of 4 seconds. So, and then what we do, we then stop the excitation after 4 seconds, and then the system would vibrate freely after that point, right, and then we measure the free decay responses during that interval, right. So, this is a schematic of the how the structure is excited and how the responses are measured. So, you can see at point number 2 and point number 5 we have applied the excitation, white noise excitation, and then we are measuring the response rate at all the 5 points simultaneously. Okay, at all the 5 points we are measuring the responses simultaneously. So, you can see this is a plot of the excitation being applied at point 2 and 5. So, you can see this is the excitation at point 2, this is the excitation at point 5, and what we note for up to 0 to 4 seconds the excitation is applied and it is a random excitation, right. Okay. And then after 4 seconds the excitation is stopped. So, there is no excitation applied after 4 seconds, right. So, what kind of response such an excitation results? So, there are two such responses shown here, response at point number 1 and response at point number 5. Okay. So, what we note that for 0 to 4 second there is a random excitation of the system, and hence there is a random response. So, it is a forced response of the system because in this duration the continuously the excitation force is acting on the system, right. But after 4 seconds there is no excitation, and therefore the structure vibrates freely after 4 seconds. So, you can see this is nothing but the free vibration response, this is nothing but the free vibration response. Okay, this free vibration response. So, now we would measure the free vibration response as we want to measure the free decay response, right. So, now we measure the free decay responses at all the 4 points. So, this is what we measure at point 1 and 5. So, you can see this is now the response is continuously decaying, right. So, this is nothing but the free decay response. So, we have taken a record of 4 second length at all the 5 points. Okay. And now these are the free decay responses which will now be used to construct the Hankel matrix. So, in this case now we have the matrix of free pulse responses or matrix of free decay responses. It is of order 5 into 1 because we have one set of excitations being applied, right, and so and then the responses are measured at 5 points. So, it is the matrix Z is of order 5 into 1, and now we take 164 number of instants, okay, 164 time instants we take, okay, in the measured response time history, right, and that makes the first row of the Henkel matrix, okay. And then we construct such R 130 number of rows, okay, and so that gives us an Henkel matrix of size 650 by 164, okay. So that is the size of the block Henkel matrix. Now we perform the singular value decomposition of this block Henkel matrix, and then we drop the 0 and near 0 singular values, right, and then truncate the singular value decomposition. So we plot the singular values of the Henkel matrix, and this is the plot of the singular values of the Henkel matrix. So on the y axis the magnitude of the singular value has been shown, and we have shown here the top 50 singular values of the Henkel matrix, and what we observe that the first 8 singular values they are significant, right, they are non-zero, and after that the singular values are either 0 or they are nearly 0, okay. So therefore from here we understand that there are only 8 number of significant singular values. So rest of the singular values we drop and we only retain these 8 singular values, okay. So therefore the system order is 2n is equal to 8. So there are 4 physical modes which are there, right. So now we compute the state matrix A from the expression we derived earlier, and then we find eigenvalues and eigenvectors of the A, okay, and then from that we find the eigenvalues and eigenvectors in the continuous time. In the first table, so the first column shows the pairs of the complex conjugate eigenvalues or poles we got, right. Second column shows the estimate of the natural frequency from the poles, right, and the third column shows the modal damping factor for different modes. And then we also get the mode shapes corresponding to these poles which are shown in the this table. So here these mode shapes you obtained, they are unscaled mode shapes, they are not mass normalized mode shapes, okay. So you can see here they are unscaled mode shapes, not the mass normalized mode shapes. That is because the excitation that was applied, okay, it was not in the form of unit impulse, and it was an excitation which was different than unit impulse, and that is why the scaling of the mode shapes cannot be realized through estimation. So there is an unknown arbitrary scaling factor associated with the modes that have been obtained. So in modal parameter estimation, one of the issues is to decide that how many modes that exist and which need to be identified through curve fitting, and that is also known as what modal order we want to estimate, right. For example, in the ERA we wanted to identify the state matrix A first, and the question was that what should be the order of the A matrix that we want to identify, okay. So in the ERA this issue was resolved based on the singular value decomposition, right, and then the minimum realization was sought. So similarly in other modal parameter estimation methods, it is necessary to know, or it is necessary to decide that how many modes we want to identify. For example, in the frequency domain method also we would like to know that, okay, how many modes we want to fit in the selected frequency band, right. So several approaches have been followed and proposed which can be used to decide the modal order or the number of modes which exist or which we need to identify or we want to identify through modal parameter estimation. So the first approach has been to count the number of peaks in the FRF. This is probably the, I think, the most straightforward thing to do, right, that we look at the FRF of the system and then we count the number of peaks in the selected frequency band. Many situations this will work, but in many situations it may not work. For example, if there are many closed modes, right, then it may not be easy to decide on the number of peaks. If there is noise in the data, then the noise may sometimes be interpreted as a mode because it may give rise to a peak in the FRF. Also, when the damping is high, then the peaks may not be prominent or they may not look very sharp, and then the question would be there whether there exists a peak or not. Therefore, counting the number of peaks may not always give accurate estimation of the modal order or the number of modes which exist in that frequency range. The other approach that has been used is to overlay all the measured FRFs, because when we overlay all the measured FRFs, we would be able to see very clearly the peaks in all the FRFs. And the overlay ensures that all the peaks which consistently appear in most of the FRFs or all of the FRFs, they are prominently shown in the overlay plot, isn't it? And therefore, based on that, then we can be certain that which are the true modes and which are not the true modes. So, that is also an approach that has been used to determine the model order. The other approach that has been used is use of a stabilization diagram. So, let us look at more closely what is stabilization diagram. So, stabilization diagram is essentially a plot of the model parameters that are obtained by curve fitting using various model orders. Okay. So, idea is to repeat curve fitting with various model orders starting from a high to a low model order. So, we start from a very high assumption of a high model order and we perform the curve fitting and we identify the model parameters. And now we reduce the model order and repeat this curve fitting process, yielding another set of model parameters. And this process is repeated for several model orders going up to a low model order. And all these model parameters then are plotted against the model order. As the model order is reduced, right, the model order of true modes they stabilize, while those of false or computational modes they fluctuate and gradually disappear. So, when we plot, let us say, natural frequencies identified using various model orders. Okay. So, what is going to happen is that the natural frequencies which represent the true modes of the system, they are expected to consistently appear in all the curve fitting runs with various model orders. But the ones which are false frequencies, which do not represent the true physical modes of the system, their value would fluctuate from run to run, or they would drop altogether from further runs. So, such natural frequencies do not represent the true modes of the system, right. So, in this way the stabilization diagram helps to identify or distinguish between the true modes or the true model parameters and the model parameters corresponding to computational or noise modes. Okay. So, therefore, the true model order is the lowest model order where the various model parameters have stabilized. Let us look at a plot of stabilization diagram obtained by curve fitting for a typical system. So, you can see here on the y axis we have the model order, on the x axis we have the natural frequencies, is not it, and various dots here show the estimates of natural frequencies identified in curve fitting with a particular model order. For example, when the model order chosen was 20, so these are the natural frequencies that were determined. Okay. So, so many natural frequencies were determined. Okay. So, you can see there are 10 number of natural frequencies because there are 10 number of physical modes when order is 20, right. Similarly, when 18 is the model order, these are the natural frequencies that were estimated, 9 number of natural frequencies. So, in this way we go up to, say, in this example we have done the curve fitting up to model order 2, that is only one physical mode that was identified, like this one here. So, what is the observation? So, we see that for example, here this frequency this consistently appearing here. For example, you can see all these frequencies are consistently appearing in all the runs, right. Similarly, these frequencies, this natural frequencies also consistently appearing in all the runs. So, these frequencies are expected to correspond to the true physical modes of the system. But if you look at other frequencies, for example, if you look at this frequency, so this frequency has changed to this one and there is a fluctuation, and after that it does not appear at all. So, these frequencies therefore are not expected to represent the true physical modes of the system. They basically represent the computational modes or poles of the system, because in curve fitting the algorithm will try to feed the data as close as possible. So, in the process it may assign computational poles to the system which are not the physical poles of the system, right. They have been just assigned or used in order to obtain a good fit. So, such poles are referred as computational poles or noise poles. So, therefore, with the stabilization diagram we can make a distinction between the true poles of the system and the physical poles of the system, right, and then we can decide the model order. Okay. So, in this case, for example, we see that the 4 frequencies they have stabilized, right, and they consistently appear in different runs, and that is why there are 4 natural frequencies of the system and there are 4 physical modes which are the true modes of the system in this frequency range. What are the observations based on the different model parameter estimation methods we have studied? So, the first observation is that the single degree of freedom methods, they can provide reasonable estimates in cases with well separated modes and modes with smaller damping, correct. So, in this case the single degree of freedom assumption would be valid, and then they can provide reasonable estimates of the model parameters. Now, multi degree of freedom fit would be necessary with closed modes and modes with high modal coupling, because in such cases the single degree of freedom assumption would not be valid, and therefore multi degree of freedom fit would be essential. Also, the frequency domain methods, they provide insight into the curve fitting process, because we perform fitting in the frequency domain. So, we can see that how the curve fitting of different peaks and the modes in the FRF they occur, right. So, it provides say insight into the curve fitting process, but the time domain signal is a complex varying signal, right. It varies in a complex manner. Contributions of different modes, they cannot be visibly seen in the signals, and that is why it does not give the insight which the frequency domain methods provide. Single degree of freedom fit is possible in the frequency domain, but not in the time domain. So, in the frequency domain we can see that okay, in a certain frequency range a particular mode dominates, right. So, if you choose a frequency range around a particular peak, then in that range that particular mode dominates, but the same thing cannot be said in the time domain, because the different modes make contributions at all instants of time, okay. So, therefore, there is nothing like single degree of freedom fit in the time domain, right, because we cannot say that okay, in this time range only particular mode dominates. No, it is not so. At all times all modes are contributing in general, but in frequency domain we can choose certain frequency range in which only a particular or only a couple of modes dominate, right. Now, many time domain model parameter estimation methods can use free pulse responses, and hence can also be used in output only model analysis, right. So, time domain methods, their formulation can also be used to process the responses which are free decay responses, okay. And like we saw the ERA method, it could process the free decay data as well, and therefore many time domain methods can also be used where only the output responses are available and the information about the inputs it is not available. So, so those methods are basically called output only model analysis methods. So, the many time domain methods can be used for performing output only model analysis. So, in this way we come to the end of this lecture. Today we talked about model parameter estimation using time domain methods. Now, we stop here. Thank you.